And we are recording. I will full screen my own screen so I can see what's happening. There we go. Okay, so to pick up where we left off yesterday we introduced the concept of elastic collisions. Elastic collisions defined as the idea that we could have a collision where all the kinetic energy is conserved in the two or three or however many macroscopic objects that collide. Now, and I'm being specific here just as a little side note, because earlier on we said, well, if we have a completely inelastic collision where the two cars, for example, that Alex and Octave were driving got embedded in each other, a lot of energy went into heat and went into changing the temperature of the air. Well, of course, when the temperature of the air changes, the molecules in the air are actually traveling faster. So the kinetic energy technically is conserved there as well, right? Because the energy went into the air in the form of kinetic energy of the molecules. So it didn't get lost, of course not, because energy is conserved. But we're specifically looking at a situation where the kinetic energy of the macroscopic objects is conserved when we're looking at an elastic collision. Now, we wanted to take our result from yesterday that we had and actually just take a step back and make sure that it actually worked. And this is actually a good tip, because if for some weird reason, maybe a hateful physics teacher, those kind of things, you are actually faced with having to do an elastic problem and you've done that and you notice it was a little bit tricky, even with the trick that we used to make the math easier, it's still pretty schnickely in my opinion. So after you get the result, you might want to plug it back in just to check that kinetic energy actually was conserved and maybe even that momentum was actually conserved, because it's super easy to make a sign mistake, as I proved yesterday in this kind of calculation. Okay, so let's go back and actually take what we have as our results and see in a double checking sense that actually momentum is conserved and that kinetic energy is conserved, and let's move on from there. So I still have the calculation on the board, and we can take the info and copy it up here. We have this stuff over here, which was our starting conditions, and we can maybe just take the other information that we have here. Here's V2 on the screen here. Whoop, there we go. There's V2 down here. There's V1 over here. We can maybe just make some room over here to just bank that info over here. So we got V1, and we found it to be 13.9 meters per second. Sorry, V1 is 7.5 meters per second. That's the final speed for V1. And then we have V2 being 21.4 meters per second. And I'll draw the line down here. And now we're going to take everything else and just erase it. And now we can just double check to make sure that in this collision, actually momentum is conserved and kinetic energy is conserved. So let's make a little table. And we've got here, let's start with momentum. So here we go. So we have P10, we have P20, and then we have P1. Oh, then we have, of course, this seems kind of silly because P10 is, of course, P1 total. So we don't have to really calculate the other two. Okay, let's just do that right away. So initially, only object 1 is moving, and object 1 was Alex's car at 3,000 kilos, the Hummer, and his velocity was 13.9. So let's put that in there. We got 3,000 times 13.9, and let's just double check that to make sure it actually does work out the way we think it should work out. If I put that in my calculator, we get 3,000 times 13.9. I get 41,700. And for the unit on that, it's kilogram meters per second. There's no separate unit for momentum. And let's take a look at P1 and then also P2, right? And then of course, those two added together should be P total, the total momentum after the collision. So this P0 total was the total momentum before the collision, and this should be the total momentum after the collision. Let's take a look at P1, of course. We have 3,000 now times 7.5. 3,000 times 7.5, 21,000, 22,500. Okay, we got that. Kilogram meters per second. And then for P2, we got the second mass, which is 900. And we've got a velocity of 21.4. And that's doable in my head, but I don't feel like it. So let's just do that with the calculator. We get 19,260, 19,260 units kilogram meters per second. So we add those two together, here, this one and this one, we get 41,760 kilogram meters per second. There we go. And we see that the momentum is conserved. Just making sure we're right on here. So we see here's the original momentum and here's the momentum after the collision. So momentum is conserved. So that's good news. So let's put a little line in over there. And let's take a look at what's going on with the kinetic energies. Okay, so we have here kinetic energy initially, of course, is just the kinetic energy of object 1. Object 2 is not moving. Then we have kinetic energy total, because it's the only one initially. There we go. And it's 1/2 mv squared. And we've got just mass 1, which is 3,000, 1/2, 3,000. And then the speed V10 is 13.9. And again, because we're Americans, we're not squaring that. And we're not using the units in there. And I'm going to punch that in my calculator. And I get out 290,000 joules. We did this before. I'll just write it like this, make it a little easier, 290 kilojoules. Okay, and now let's take a look at our other two kinetic energies, the kinetic energy of object 1. After the collision, we're looking at the mass of 3,000 and a speed of 7.5. Again, the same equation, 1/2, 3,000 times 7.5 squared. Punch that in our calculator, about 50. About 75,000, we get 84,000. Okay, so we get 84 kilojoules here for the kinetic energy of object 1 after the collision. And then let's take a look at the kinetic energy of object 2. And of course, 1/2 mass, 900 times V2 squared, which is 21.4 squared. We punch that in our calculator. And that actually ends up having 206 kilojoules. That's interesting. It's way more kinetic energy in this case. But in total, right, if we take the total kinetic energy after the collision, it's 206 plus 84 is 290 kilojoules. Okay, well, that means that in total, these two objects have 290,000 after the collision, and that's the same energy our first object had before the collision. So kinetic energy is conserved. Boom, that's the result we have. Okay, so on this. Yes, hello?
Am I reading this right? The initial total momentum is 41,700, but the final total is 41,760.
Yeah, that's a rounding thing. So yes, you're correct that for a mathematician, those numbers are not equal, but for a physicist, we'd be like, oh, whatever, that's like off by like 0.15% or something.
All right.
Is that cool? Yeah. Yeah, that's a rounding thing. So I just, being a physicist, I'm like, those are equal. So if we carried more digits, but then we'd have to carry a lot more digits here. So when we actually, for example, converted this here and when we converted got these numbers because we only have 2 sig figs to get all chemistry on you, right? There's if we'd have to carry at least 1 or 2 more digits, and then that would we get rid of that, and it would be, you know, we can get it as close as we want, but definitely because we're looking at the last digit, this is equal according to, you know, how we think about things being equal. And then here also, actually, I'm kind of, let's go down here to kinetic, oh, there it is. So for the kinetic energy, the opposite is true, where if we went like more digits, eventually we'd probably, not just probably, we would find that they don't agree anymore. In this case, it adds up perfectly, but they don't add up to the single joule, again, because the numbers we have are rounded. So they're not perfect, but they are equal enough. Okay, cool. So nice. We have now our result for the transfer. So here is our elastic collision, and it works out all nicely over here. I'll take a picture of that and I'll post that to the group, and maybe I'll just write over here, checking that P and K are conserved. That's what we did, and that's what the purpose of this thing was. And we'll take a little picture of that and post it over to our AP Physics group. Come on, there we go. And I'm going to turn it a little bit to get that shot. And voila. Okay, there we go. That goes over there. Nice. Good. So I'm going to erase all this stuff here. Okay, we got that. So we have our, here's our, so let's just see what we have here. So we had our stuff here. That was our initial conditions, right? And these were true no matter what. And then we had down here our elastic collision, our results. Okay, and we also had from our previous day, we had completely inelastic. Again, a reminder, that is kind of our option 1. This is our option 2. We'll get to option 3 in just a second. But just a reminder, what we had here for the completely inelastic option, we had, this was yesterday. All my troubles seem so far away. Now it seems like they are here to stay. Okay, so let's take a look at what we have there. So yesterday, we had kilometers per hour. Here we go, 13.9, and then it was 10.7. So here, for completely inelastic, here we go. Here are our results. We had V1 equals V2 equals 10.7 meters per second. Okay, cool. And we had a loss of kinetic energy of 23%. Okay, so that was that example. So as you might expect, in a collision, because we're calling this completely inelastic and we're calling this elastic, okay, we also have the possibility that we have a collision that is actually elastic. Inelastic. Inelastic meaning not completely inelastic. So the objects don't embed themselves in each other, and they also don't preserve kinetic energy. And this will be the situation actually for most situations where you're faced with this kind of thing. Okay, so let's think about the case we had. So let's now imagine instead of Alex and Octave using normal vehicles that get crush and embedded in each other. The second case we had was they had these magical vehicles that perfectly bounced off each other using magnetic repulse systems that allow them to interact without losing kinetic energy, which is very strange. Now let's assume they're kind of like bumper cars, okay? So they do have bumpers that allow them to bump off each other, but there will be a loss of energy. So you've been in a bumper car before, I'm assuming at a carnival and hit somebody else and you bounced off them. You don't get stuck with your car in the other car, but also there's clearly loss of energy. There's noise and of course, because they're physical objects that are not interacting through magnetic interaction where there would be no loss to heat or sound, there will be loss of energy. So let's take a look here at our situation. So our situation is this, that Octave, let's take a look. He bounced off with 10 point, he didn't bounce off. He got stuck in the car, Hummer, and he was moving at 10.7 meters per second. Okay. And in the other case, we have kind of an extreme that he got bounced by the Alex's car at 21.4 meters per second. And I don't know if this is intuitive to you, but if those are kind of our two extreme cases, no bounce, smashed up, ends up traveling 10.7 meters per second, or perfect bounce, 21.4 meters per second, I would think that if it was a non-perfect bounce, that the speed that the struck object, Octave, would have should be somewhere between 10.7 and 21.4 meters per second. Okay, and this is kind of similar to, you hit a baseball with a baseball bat, and if it's a perfect hit, the ball comes off the bat really fast. But if it's not perfect, it's slower. But dude, if it's like a clay ball and it gets stuck on your bat, that will be like the minimum speed that the thing is coming off your bat at afterwards, because it's not coming off the bat at all. Same thing with, you hit an apple with a tennis racket and the apple gets stuck in your racket. And obviously the tennis ball never bounced off. The apple never bounced off the tennis racket. Same thing here. So Octave is essentially like the ball being struck, and he only is going 10.7 when he gets stuck in the Hummer. When he's bouncing perfectly, he's going 21.4. But any number between 10.7 and 21.4 is allowed according to physics. Okay, that's our third possibility. In those cases, we're looking at an inelastic collision. So let's just pick this value somewhere in the middle. For example, 15 meters per second. So let's say Octave is struck by this interaction, and afterwards he is traveling at 15 meters per second, which is why in the context of our class and physics in general, well, I don't know if everybody uses this term, but I use this term, this third category of inelastic, I also call the given category. Because remember, we were in the situation where we needed to have an additional piece of information to be able to solve the problem, because conservation of momentum was not sufficient for us to solve the problem, because we only had in that equation, we still had in that equation two unknowns, V1 and V2. Now, if we give V1 or V2 after the collision, then the problem can be solved. So let's write that down. We're going to say, okay, we're given V2 is equal to 15 meters per second. And now everything else should be easy to find, because now that we know V2 is 15 meters per second, we just have to use conservation of momentum to find V1. And then we can also find how much kinetic energy is lost. Let's try this out. So we have still our situation. Octave and Alex are striking, well, Octave's being a good boy, is waiting at the Ampere, but Alex is running into him, and we have the momentum. Let's write it out this way. So we have momentum initial equals final momentum. It is a collision, so only the interactions between the two objects matter. Reminder about that idea, because the force of 1 on 2 and the force of 2 on 1 are equal and opposite, the total force is 0. The total force is 0 the entire time due to Newton's third law. Because the total force is 0, the impulse delivered is 0, therefore the change of momentum in total for the two objects is 0 and momentum is conserved. So momentum is conserved, P10 equals P1. Let's write that out. We know that M1 V10 is the only thing that's moving before. Afterwards, M1 V1 is moving, but M2 V2 is also moving. Let's plug in the values. For M1, we got 3,000. We got V10, we got 13.9. Again, Americans don't need to write down units. M1 is 3,000. This is the value we'd like to know. We don't. Octave is going at, it has a mass of 900, and afterwards he's traveling at 15 meters per second. So there we go. We can solve this for V1. So V1 is equal to 3,000 times 13.9 minus 900 times 15, whole thing divided by 3,000, solving this equation for V1. There we go. I hope that makes sense. So we moved this over to the left side. There it is by subtracting it, and then we divide by the 3,000 to solve for V1. And let's plug that into our calculator. And let's see where we are. So 3,000 times 13.9 equals minus 15 times 900 equals divided by 3,000. Boop. I get 9.4 meters per second for the speed of Alex after the collision, 9.4 meters per second. So now notice that then Alex's speed of 9.4 is also in between the two values for Alex's speed. For Alex, we had that his speed had started at 13.9, and either it dropped to 7.5 or it dropped to 10.7. Those were the two possibilities. And not surprisingly, again, for this situation, which is in between the elastic and completely inelastic situation, Alex's speed should also be between those two values. And in his case, it will be 9.4 meters per second. Now let's take a look. You might ask, or a physics test might ask, is kinetic energy conserved in this case? Well, probably not, especially because we already calculated the elastic collision, and we got a different value for the speed, so it shouldn't be conserved. But let's double check to make sure the kinetic energy indeed is not conserved. So let's do that, and we can skip, obviously, the kinetic energy initial, because we know that's 290,000 joules. We did that several times now, and now we're just going to double check what kinetic energy is in this case. So kinetic energy of the first object, or we can just write it together. Let's do kinetic energy total equals K1 plus K2, the kinetic energy of our two objects together. So that would be 1/2, 3,000 for the mass of object 1. Our speed is 9.4 squared. It's a little tight back here, but I think we can get this down. 1/2 900, and then we need to plug in the speed that was given from the start, which should be 15 squared. Okay. So we have 1/2 3,000 times 9.4 squared plus 1/2 900 times 15 squared, which is Octave's situation. Let's plug the values in and let's see what we get. 9.4 squared times 1,500. For the first one, I get 132.5. I'll carry another digit there. Why not? Plus, And then we have the other one, 15 squared times 450. I get there 101.3 kilojoules. Okay, and I get 233.8, 233.8 kilojoules. 233.8 kilojoules. Okay, so let's take a look. We have 233.8 kilojoules, and we're on screen. Yes, we are. We have 233.8 kilojoules, so the energy is not conserved, okay? Because we started with 290 kilojoules initially, and some of that energy was lost. Okay, 233.8, and just to see where we are on the previously discussed problem, we ended up having 224 kilojoules, so less energy was lost in this case, which makes sense, again, because effectively the most devastating, most crushing situation, obviously, in certain ways, is when you have a completely inelastic, and therefore the kinetic energy loss is maximized. And the maximum was 24% that we listed previously. In this case, less kinetic energy is lost proportionally. Okay, oh, see, 23% before. Now we have less loss. And let's actually find that number. And because we all love when we can squeeze things in, just really, really small here, percent kinetic energy lost, squeezing that underneath, 233.8, let's say 234, just to make the math easier. Out of 290, where we were, that means we've lost 56 kilojoules. So 56 divided by 290 times 100%. So 56 divided by 290, I get 19% lost. 19% lost. Okay? And which is less than what happens in a completely inelastic collision. Okay, so let's scroll back up here. Here we go. And I'm going to take a picture of this and send it to you. There we go. All right, here we go. I got a message from somebody. Hello. Oh, wait, what? No. Oh, no. No message. Okay. Okay. Cool. So nice. And I'll erase this stuff down here. Okay, and here we go. And I'll erase this stuff as well. Okay, good. So let's actually just kind of summarize then what we just found. What did we just find? We found, first of all, if F external is equal to 0, if the sum of the external forces is 0, and again, we're being pretty loosey-goosey here, that also means basically they are negligible, then it should be true that momentum is conserved. And this, of course, is a restatement of Newton's first law. So effectively, what we're doing is we're looking at Newton's first law saying, if there's no external force, then mv is the conserved for the whole sum of all objects together. And we can formulate that like this, specifically for 1D, 2 objects, which is kind of a subcategory, obviously, because you could have 3 objects, 5 objects colliding, and they can collide in 2 dimensions or 3 dimensions, whatever. But oftentimes we'll look at just those 2, and if we do that, we get this equation out of that. Okay, here it is. Here's our equation to summarize that, so this is equation 1. And then we need a second equation. Okay, and for our second equation, we have 3 different cases. The 3 different cases being, okay, elastic collisions. Oopsie, sorry, that's the wrong one. Completely inelastic. They stick together. They are embedded. They travel together. Those are kind of the phrases you should be looking for to make sure that you understand that the question is saying that the problem is completely inelastic. You should say something like that, such as one car strikes another and the 2 cars travel together after the collision. The bullet strikes the block of wood and is embedded in the block of wood, and they travel together after the bullet hit the piece of wood. The linebacker ran into the quarterback, wrapped him up, and after the collision, they are flying through the air together. For example, if you want to do a classic American, they always like doing football problems. So there you go. So embedded, travel together, boom, there you go. And that, of course, means in each case that V1 is equal to V2 is your second equation. Okay, that's for that situation. Then situation 2 is elastic. And how do you know it's elastic? Well, if they say the collision is elastic, and sometimes they actually misuse this word completely and just say the collision is completely elastic. Well, that's kind of redundant because elastic is elastic, period. And that's just what it is. Elastic is elastic, boom. So elastic collision means that, well, it means kinetic energy is conserved. That's another way of saying that. Kinetic energy is conserved is another way of putting that. And I'm going to introduce one more way of introducing this concept, and that's introducing a specific phrase, and that's the coefficient of restitution. And the phrasing is the coefficient of restitution is 1. And this vocabulary word, coefficient of restitution, wow, you should ask for a discount on your tuition based on lack of good handwriting here. So restitution is 1. What is the coefficient of restitution? The coefficient of restitution is equal to the final kinetic energy in total divided by the initial kinetic energy in total, by definition. So as you can see, if the final kinetic energy is equal to the initial kinetic energy, well, then the coefficient of restitution by definition is 1. A few minutes ago, we saw that 23% was lost in one collision. And that, of course, would mean 23% is lost. It means the final kinetic energy is 77% of the initial kinetic energy. So the coefficient of restitution a second ago for Octave and Alex's first collision was 0.77, for example, and not 1. It always has to be less than 1. Well, it should be less than 1 unless there's something goofy going on, like there's an energy source contained. Oh, we should introduce that later. Okay, anywho, so there we go. And let's scroll down here and then come down through our third possibility. So how do you know when it's neither completely inelastic nor it's elastic? How do you know that's true? Well, a few things. First of all, the problem will normally list a given. So it will say something like the bowling ball strikes the bowling pin. The speed of the bowling ball before the collision is 12 meters per second, whatever. And the mass of the bowling ball is 6 pounds, whatever. It strikes a bowling pin with a mass of 2 pounds. And after the collision, the bowling pin is traveling at a speed of 36 meters per second. That seems like kind of fast. But anyway, you get the idea that they give you that answer, then generally you know, oh, we're in this category. But not necessarily, because you could be facing the evil physics teacher, evil physics question writer situation where they give you the final speed of one object, such as of Octave's car, for example, but actually it is elastic. That's unusual, but it's theoretically possible. They tend to not do that just because we're not that hateful, even though you might think we are. So probably unlikely, but you must be prepared that if it is given, then it could be one of the two other categories, but you could easily check that because, of course, if you have the speed given for Octave in this case, and afterwards you find that Alex's speed is exactly the same, well, hello, that's V1 equals V2. The two are traveling together. And if they give you a speed for Octave and you calculate the speed for Alex after the collision, and then you calculate the kinetic energy in total, and you find, whoa, the total kinetic energy is still 290,000 joules. That means kinetic energy is conserved. And that, of course, would mean then that this collision is indeed elastic, even though it was told to you as a given situation. Okay? So this is a given situation. You know it's because something is given. And also you know it's this because it is not stated that the collision is in category 1, which is completely inelastic, or it's not stated that it's elastic. So if they don't say that, if they don't say it's elastic, then it's not elastic. So if they don't say kinetic energy is conserved, normally kinetic energy is not conserved. And if they don't say that the collision is completely inelastic, that they're sticking together, but they say the bowling pin afterwards is traveling at a certain speed, then this is a given situation. So you need to use that approach to find the correct answer for your problem. Okay, good. Let's scroll up over here. There we go. Let's take a picture of this board. Wow, this handwriting is really deteriorating over here. And send that picture over there and send that in the group. Okay, so here we go. And we're almost at the end. We only have 5 minutes left. So we have our 3 situations summarized. We have up here Newton's first law summarized. And the last thing, and this is where we're going to go next. The next thing, we've got a few things left to do, and we are having class on Monday in person, most likely. That's what it looks like. So we're going to next look at this equation right here a little bit more in detail. And what I mean by that is we've really thought about this equation mostly in the context of where the force is 0, the impulse delivered is 0 for both objects together. And then, of course, t was completely irrelevant because 0 times whatever is still 0. But if we now look at just one object, Octave's car or Alex's car, of course, the force on each of those is not 0 on average. It has a specific value. And it's a very, very interesting value, actually, because it will tell you how dangerous this interaction is. So how dangerous is this interaction to Alex? How dangerous is it to Octave? It's important to know how much force is exerted on the car, how much force is exerted on the inhabitants sounds really stupid. The people in the passengers and the driver in the car is really important. For that purpose, we'll need to know T. We can right now already figure out the impulse delivered to both cars because we know their initial and final speeds. But to find the average force on either car, we have to know the time. And we have ways of getting at that, at least an estimate. And we can talk about this next time, but that's where we're going next, is to look at this equation and think about how we can relate impulse delivered to the time it takes to apply the force and to the force. So how are these 3 concepts connected, and how can we figure out how much force is involved in a collision? Okay, so I will stop the video recording.